Okay. Okay. Does it work?
Yes.
All right. Hello.
Okay, so obviously we cannot finish this overview without perovskite. I am glad to introduce Philippe Schulz. He's a CNRS researcher at IPVF, Institut Photovoltaics d'Île-de-France. I would say French.
Right.
He's an expert of perovskite, also of interface and characterization. So he will give another talk tomorrow.
Yes.
This one will be a short talk, about half an hour.
Half an hour. Okay, because I'm listed at 45 minutes. So.
Okay, so this is the 45 minutes.
Okay. It's all right.
The organization is like solar cells, it's not ideal. So 45 minutes, no more.
Okay, sure. Yeah, first of all, thank you very much for the invitation. So it's great to be here. It's great to be back. So from 2 years ago, apparently, since I'm invited again, I guess last time wasn't a complete failure from my part. All right, just as Stefan said, I'm the last speaker today. So yeah, it's supposed to be 45 minutes, but since I'm the last speaker, there's that. No, I keep to the promise. Maybe I want to, this is very much in the spirit of the other technology talks that you had before. We'll talk a little bit about the materials properties, but also about the history, how these materials came into being, how these solar cells came into being. And I want to give you a very short overview of our Institut Photovoltaics d'Île-de-France, where I work as a CNRS researcher, as Stefan has pointed out. We are located at also on the Paris-Saclay campus, so you've seen this view graph here before, this picture by Andrea Catoni. So we're neighbors in this thriving new community neighborhood with technology institutes and schools. So we are a dedicated solar research platform for institutes that were, of course, already existing and that were already working on solar cells, but now come together with one joint mission and under one roof. And it's also a public-private partnership, so we really have in focus going from fundamental science to the application, and also enabling a Center for Research and Industrialization, which is given by, as you can see here, the industry partners and academic partners that found together. And this is our research program. We do have, we do everything, so to say, from economic market assessment over different technologies. Stefan is actually leading this program, 3 low-cost 3.5 on silicon tandem cells. I'm involved in mostly in program 4. Jean-François is head of the new proof and concept breakthroughs. I think you will hear a little bit about this on Friday, then in the morning. All right, but now, yeah, I said that. Okay, so okay, so it's. Let me go back to this one. It's the last talk of the day, so maybe you are already a little bit tired, but I see everybody, the crowd is actually fresh, excited. I'm already a little bit, so probably had to process a little bit of information today. It was extremely informative. You have to carry me through the talk. As if I get tired, you have to carry it through. So first of all, I deviate a little bit from the promise in the title. I will talk about emergent solar cell technologies in general, which means that I will give a brief history of organic photovoltaics. First of all, because this is where I come from scientifically, on my academic education, but it's also really the precursor for perovskite materials and perovskite solar cells. Of course, perovskite, particularly these halide perovskite, there has been research, fundamental research already in the 70s, 80s on this. It was until the 90s that they found widespread use, or no, that's actually not the right word, more focus on their optoelectronic applications. Back then it were transistors, famously looked at by David Mitzi and Sherry Kagan, and not then unless until 2009 that the first perovskite solar cell made its debut. It was derived from the dye-sensitized solar cell, that's why I have this in this list here as well. And we will discuss, of course, the development of how we got from the dye-sensitized solar cell to today's high performance and also high stability perovskite cells. Followed by the basic concepts of perovskites, and then, we will probably not talk about this, but the quantum dot solar cell field is now also being rolled up by perovskite materials, of course. So, emergent PV technologies. First of all, who of you is familiar with this topic? So, yeah, right, audience participation. Who of you works on perovskite solar cells or organic electronics? Please, a show of hand. Okay, so this is actually quite substantial amount, so very glad to have you here in this crowd. I want to start with this very short start here. Organic is not equal bio. Organic means hydrocarbon, bio is life. If you're just plain English speaking, this seems to be a little bit weird, but me as a German, and I think this is a conception that can also exist in French. What you buy in the supermarket is the healthy food is bio in German and also in French, but in English it's actually organic. So and of course organics come from biomass that has been degraded and so on and so forth. In any case, anyways, we talk about these complex organic molecules, and you can see the molecule is a very basic fundamental building block for your electronics, which means you can substitute atoms with a very high precision, chemists do that, and tailor the optoelectronic properties. And you can see this here if you look into the optical properties of molecules that can make very bright dyes depending on how you choose your molecular structure. And I will show this a little bit more detailed further on, but let me first assure you, yes, organic electronics are there, they are on the market. Displays are being made, OLED displays famously. Plastic electronics wanted to enter the market also with lighting application, displays that you probably have in your phone, and also for flexible electronics. So what you can see here is an RFID tag from organic materials, which means that you can bend it and also produce it at very cheap cost. This is the big promise, and we will see on how much this holds true in a little bit. But bendable and flexible displays are on the market, and of course this now opens up an avenue to make flexible solar cells. There we are as well. So this is probably not the best example because I think the company went bankrupt, or so I thought, but they are actually still there, though they are not making these kind of products like solar cells that you could integrate into clothing or your or a tent, but actually for materials that organic solar cell makers can use. All right, and with this I give you this very short history about the development of these technologies. So photoconductivity on organic solids was already found very early on, and just around the last century, over a century ago. It was a little bit more difficult to find dark conductivity on organic single crystals. And the key here was that you actually had to go to very high material quality in order to see electrical current flow through the crystal. And for this you had to develop purification processes corresponding to zone melting, but it's rather a physical vapor transport process. The conductivity in polymers, so rather disordered organic materials, was then discovered in 1977 and was awarded the Nobel Prize about 2 decades later. And we then come to the first heterojunction organic photovoltaic device in 1986. And this is notably before the first OLED has been made. So the organic solar cell was actually there before the first OLED that is now on our devices made it, saw the light of day. So this is it, and the first OPV, however, from solution processing, and this is really one of the promise that it's a very cheap process because you can print it like newspaper, was in the 1993, and then the first certified organic solar cell with 2.5 power conversion efficiency made it into the NREL chart in 2001. So as I said, the big promise were these unique properties of organic materials, that they are soft, flexible, lightweight, inexpensive, and earth abundant. We had Christine is around here, so we had a very interesting discussion over lunch about the cheapness of organic materials and the earth abundantness and so on. So there are some chemical synthesis steps that are quite expensive behind it. And so I just told this small anecdote to my group. I think last week when I was still doing my PhD, we were working on organics, and there is a way to evaporate organics. So you have your crucible, you have the powder in there, you melt it down, and after that you reheat it in order to evaporate. And so there was a big machine in a company that I won't name today, and they had this powder in there, and then one technician accidentally vented it, and the entire powder flew through the machine to all the chamber walls and so on and so forth. So any idea on how much this accident actually cost for the few grams of blue dye that was? So, say again? I heard. Almost there, 50,000 euros just for one, for one small boost of nitrogen through your system. Okay, so now let's go to the inner structure of organic molecules. And again, this is not just for OPV, but also for perovskite solar cells. You need this kind of understanding, because you still use organic materials as transport materials in perovskite solar cells. If we can ever get away from this part is unclear to date, but there is simply not a pure inorganic perovskite solar cell that is working fine. So here you see the inner makeup of the benzene ring that is bonded strongly by these intermolecular bonds, this sp2 hybridized carbon. You have the pi orbitals forming a ring-like delocalized pi electron cloud on this structure, and depending on how you connect those rings, you make even a larger, a smaller or a larger potential well, and therefore get different energetic transitions or electronic transitions for your optical excitation. So in contrast to these very strong intramolecular bonds that tailor the optoelectronic properties, we have the intermolecular bonds. Those are very weak. They are van der Waals bond. There is hydrogen bonding also involved in this binding scheme. But this give organics the soft matter properties and also the mechanical flexibility. With this, there are a few important terms to keep in mind. It will become extremely important when we go to the interface lecture tomorrow. These are energetic. So we are operating here on the energy scale. This is the vacuum level and the Fermi level. And typically for a semiconductor, you have unoccupied state and occupied states. The difference between the Fermi level and the vacuum level is the work function. And then the LUMO is the lowest unoccupied molecular orbital. It corresponds to the conduction band in your inorganic solid, whereas the HOMO is the highest occupied molecular orbital, which corresponds to your valence band. So why do we do this, make this differentiation? That is because these electronic states are still localized and exhibit very flat bands. So you almost have the discrete energetic transitions compared to a band structure that has a high curvature of bands. But nonetheless, make no mistake, they correspond to the conduction band and valence band. Now this is how an organic solar cell works in general. We call it an excitonic cells for reasons that will become apparent in a second. So first we have light absorption that generates an exciton. So this is not a free, these are not free carriers, a free electron and a free hole, but this is actually tightly bound, so-called Frankel exciton with a binding energy that is higher than your average KT, so on the order of hundreds of milli-electron volts. And after this exciton, which is electrically neutral, needs to diffuse to this interface between a p-type and an n-type organic material. In organic solar cells, we speak of the donor, usually a polymer, and an acceptor-like molecule. Over there, the excitons can dissociate, and you have now these separated carriers that are again transported now as free carriers throughout the solar cell and make it to the cell contacts, where ideally they are being collected at the interface. So this entire process, in order to make it a little bit more clear, we do look into the energetics of this. What you can see here is your TCO anode, your metal cathode on an energy scale. Oh, by the way, so yes, all the slides are, not all the slides are in your booklet, but they are in order. The only point is that I took some liberty, some freedom in order to add to the speaking time, to add some additional information, some additional slides, but you have the gist of the information in chronological order. Okay, moving on. I said already, the conduction band on the acceptor molecules corresponds to the LUMO level. The valence band would correspond to the HOMO level on your donor polymer. And in order to extract from here to here, you need a high work function TCO anode in general. So this is a very rough guideline. It's not that easy. We will come again to this tomorrow. And the low work function metal cathode here on this end in order to extract electrons. So if we now have excitation by light, we generate this exciton hole pair. So again, in the spirit of Uwe's talk today, I also tried to sneak in some animations. Let's see how this works out. And so we know, yes, it moved. Okay. So this exciton is now slowly diffusing to the interface. At the interface, it now dissociates and the free carriers are transported to the electrodes. So now what could go wrong in this scheme? And the one problem is that you could have carriers from one part, also here the electron going into the hole extracting contact and a hole going into the electron extracting contact, leading to recombination. And here we see a significant drop in VOC, but as been said earlier, the first thing that takes a hit is the fill factor. Now it becomes even more prevalent if you have these pathways not disconnected by an only hole or an only electron transporting material, but here in the realistic solar cell you have a bulk heterojunction, which means you actually mix your donor and your acceptor films in order to maximize your donor acceptor interface area. And now you can do this by co-evaporation or precursor mixing, but you end up with this kind of scenario here. So in red you have your acceptor, and in blue you have your donor, and you can see that each material arranges to the other electrode, and thus there are recombination pathways. Critical for the development of organic photovoltaics was to look at these interfaces and to make them selective, and it's something that is a recurring theme obviously here for photovoltaics, but particularly also now for perovskite solar cells. With this, of course, encapsulation and stability becomes an issue, but we will talk about this not today. Moving on to the dye-sensitized solar cell, which was actually there before the first organic photovoltaic cell, but works also not similar, but let me get through it. So it started off with a titanium oxide film, bandgap of 3 eV, roughly a little bit more, and an electrolyte that is also transparent. So what you have here are two materials that are just simply transparent. Now the question is, would this constitute a good solar cell? The answer is clearly not, right? So usually you want to capture light, and you do this by introducing a dye. So an organic molecule that has tailored energetic transitions to capture sunlight, generate an electron hole pair. The electron is transported away to this electrode, whereas you replenish electrons by through the electrolyte that is oxidized and reduced in the cycle with a counter electrode. A big move forward was to, and this is now critical for the development of perovskites, is to have a solid hole transporter. So to not have the electrolyte, but a material, again an organic, that is permeable for ions and also can act as a hole transporter by itself. Here you can see the dye around the titanium oxide particles. So sunlight is absorbed in the dye, electrons transport usually through the oxide nanocrystalline film, and then the hole transport through either the electrolyte or the solid state in the hole transport material. The classification is as follows. So this is really the extended family of organic electronics and, with organic field effect transistors, light emitting diodes and solar cells. And we now split the organic solar cells into small molecular cells, which are, or small molecule solar cells, usually from evaporation processes. This is really the classic pathway. It's with a well-defined molecule. And in contrast to that, the polymer solar cell, where now we use long-chained molecules. They usually have a better solubility than these small molecules. and allow large area processing. So in the site, you now have also the hybrid solar cell. So we already discussed the dye-sensitized solar cell, and then its next derivative, the perovskite solar cell. And as you can see, there seems to be a conflict. Both the polymer solar cell you can find in literature, as well as the perovskite solar cell, are abbreviated with PSC. All I can tell you is you need a little bit of context always in order to get this abbreviation correct. So in order to, Edgardo said it already today, so probably not the last time during this week that you will see this view graph. Since I used to work at NRA, I also feel a little bit obliged to bring it up every now and then. I made a big mistake, and this is, I did not look up if it was current or recent this morning. And as you know, the development of perovskites is really rapidly accelerating. We are here on orange on the emerging PV, and the perovskites starting out at what was about 12%, skyrocketed, surpassed their other thin film counterparts, except for thin film silicon, and are now at 25.2%. In tandem with silicon, earlier this year, 29.1% was reported by Steve Albrecht's group in Berlin at HZB. So this is really the axis, the trajectory that we are following, and there is, and Edgardo said it actually today already, there is no clear jump. I will bring up a slide in the end that tries to find technological breaking points, but you will see it's not as obvious as for other technologies. And then also on this view graph, you can see that the quantum dots are here, and starting from this point over here, we now also have halide perovskites permeating this axis and taking over the quantum dot solar cell world. Also very interesting, the organic solar cells have been abandoned more or less, but they had made a comeback. So they were tanking at 12%, 12 point something percent for quite a while, and now we reach efficiencies of over 17% power conversion efficiency. Key point here is that you substitute your typical acceptor molecule, which was a C60 molecule, by new small molecule acceptors that do a better job. Now, finally, to the details of the perovskite solar cells, and there I really want to start from the very beginning. Perovskite has been named after Perovsky, who's actually not found the mineral himself, but just was essentially the founder of the funding agency for the study. And it's calcium titanate. It is the perovskites that we use in solar cells are named after this perovskite material because of the crystal structure that they preferentially crystallize in their photoactive phase. And you can see it here. It's an ABX3 structure where you have a BX octahedra sitting inside an A4 cube. And the ABX3 structure defines the entire perovskite family that can be split a little bit along this scheme. So very well known, the oxide perovskite been used in piezoelectronics and other applications, also for transducers and so on. And then on this end, the halide perovskites. So the key difference here is that if the X site is occupied by oxygen, which carries 2 negative charges, for the halide perovskites, it's 1 single negative charge. And here we differentiate between alkali halide perovskites. I think it's wrong in your slides because I still wrote that the alkali should be on the B side. It's actually on the A side. And then also the hybrid perovskite, where the A side can be occupied by an organic molecule. We come to this on the next slide, where the hybrid organic inorganic perovskite, you have on the A side monovalent cation, which can be an alkali metal like cesium, but it can also be an organic molecule, small molecule like methylammonium or formamidinium. This one, methylammonium, or MA in short, was really the prototypical perovskite that led to the breakthrough, whereas formamidinium-based perovskite ink formulations make currently the most highest performant, and also most stable devices. B side is occupied by divalent metallic cation. Mostly it is lead, which is an issue in terms of toxicity. having listened to Edgardo's talk before, we at the perovskite community were always thinking to use tin in order to solve all our problems. Yeah, I don't know how I feel about this right now. Let alone that tin is not, so it has its own issues in terms of bioactivity. And I already said that the X is occupied by halide anion. Now, what is so special about halide perovskites? The optoelectronic properties are quite tunable. What you see here is the band gap. Don't pay too much attention to the electron affinities and ionization energies. They are all over the place. We'll learn this tomorrow. But what is a little bit more solidly studied is the band gap. And you can see by substituting bromine by iodine, you can lower your band gap. Then changing methylammonium by formidinium also lowers the band gap a little bit. So you can play with these constitute materials in order to quite freely tune the band gap. There are some limits, as we will see in a bit. They also exhibit a unique combination of further material characteristics, can be used in nonlinear optics, have very interesting photoluminescence properties. There are magnetic perovskites, magnetic doping, and of course semiconductivity, as I've said in the beginning, which has been explored by Mitzi et al. Now there are some additional points I want to raise, and I can't cover all of this here, but so you have, you do have the reference here on your slides. It's a paper in Advanced Materials by David Egger, who really captures on what is currently the research focus for perovskite material science. One thing on the top is that they exhibit a very high crystalline order. This is the lead sublattice that gives a very sharp Bragg peaks, whereas you have dynamic disorder on the halide sublattice. So it's not just the organic part that is, so to say, flopping around, but also the halides that are quite unstable, if you want so, related to ion, and this also plays into ion migration of those halides throughout the perovskite. Another thing is that the effective masses of electrons and holes are relatively low, and they have low density of states at the band edges. This is good because it gives you a clean edge for absorption and less recombination through defects, but it also poses a problem for one of my favorite characterization techniques, which I will explain tomorrow, because it's very hard to capture these sharp edges. You have sharp optical transitions and non-radiative recombination rates. And then a last point here that I want to raise: defect tolerance and self-healing. Given to these extraordinary mechanical properties, it is not clear what defect science looks like in perovskites. And the classical pictures, as we've seen it for CIGS and CZTS, do not seem to hold here. Even defect compensation or defect pair compensation is probably not the right way to describe it. With this, there's a broader perspective on perovskite that goes beyond the typical 3D material that has been used here, but in the solar cell mostly. But you have 2D perovskites, essentially layered cubes or layered octahedrons spaced by longer chain molecules. You can have 1D perovskite wires. These are essentially the hardest to achieve, but very interesting for lighting applications. And also 0D perovskite quantum dots, really. There are also mixtures in between where you can, for instance, start with your MX6 octahedron and have methylamine, the small molecule, and a longer chained amine, and depending on the mixing ratios, you get a 2D, 3D mixed perovskite with its own particular optoelectronic properties, and also some sort of a superstructure, assuming some structuring guidelines given by the chosen amine. So if, for instance, the molecules stand like this or shifted by 1/2 cell from each other. How do we actually find a good perovskite material, since now it seems that there's a huge zoo of possible combinations out there? There is one really critical formula that you need to keep in mind, and this is the Goldschmidt tolerance factor. That is essentially just a parameter that is given by the ionic radii It seems that there is a square missing. Yeah, okay. In any case, you need the radii of A, X, and B ions in order to calculate it. And there is a stable window within you form the cubic phase that is photoactive or absorbing on the wavelength that is interesting for us solar cell researchers, whereas deviations from this leads you in the hexagonal or orthorhombic phase, which are mostly transparent. And of course now, using all these different amines and metals and halide species, you can find combinations in which you are in the safe range. Now I want to skip these slides actually, so they are in your decks of slides, but maybe just one very small point about the rich physics in perovskites. That is, here you can see the dispersion relation, energy versus K vector of a quasi-free electron. Now, this is how you could describe the conduction band in a perovskite, also the valence band on the other side. Now, once you start exciting the perovskite, you can see a split of these bands into Rashba split components. So you get an additional term for your eigen energy values that is coming from from spin orbit coupling. This has been seen particularly for 2D perovskites, where you even see excitons at room temperature, but it also comes in 3D perovskites, and this is seen here, where you see the split of the valence and the conduction band. And this now means that after absorption of a photon and an excitation of your material, you move from a direct bandgap into an indirect bandgap. Now, there are some discussions if this is if the magnitude of the split is large enough in order to be thermally stable in the mostly used 3D perovskites, and I don't have the definitive answer of this discussion at the moment. Okay, but as I said, I wanted to split this, also this, so there can be quite interesting hot phonon characteristics. We will see, Jean-François will probably talk about hot phonons and hot carrier cells, and Daniel Suchet, so okay. I don't give it away also because I can't explain it properly. Now let's move a bit. Say again?
You distribute the word.
Yes, exactly. So that's how we thought about it. So we start with the early perovskite device configurations, and I said it already. It comes from the dye-sensitized solar cell, and the perovskite itself was conceptualized as a dye for the DSSC, and thus it was used with this liquid electrolyte, where the dye was around the mesoporous titanium oxide nanoparticles. It was actually the issue that this configuration was extremely unstable, only lasted for a few minutes before the perovskites dissociated, and you could only measure in this short time a power conversion efficiency of 3.8%. The next big step was really done by Namgyu Park in 2012. It's actually a paper that was, so if you hear him talk about how it got rejected and so on, it's interesting, given on how much impact it had. So here now they used a thick perovskite film. So the liquid electrolyte was actually removed, and you had the infiltration of the titanium oxide nanoparticles, but the perovskite itself was not just a dye, but also acted as a transport film, or at least facilitated transport of free carriers through it, then topped off by an whole transport material. And then a year later also Henry Snaith was the first to report evaporated perovskite films, where you could also make this planar structure, which again worked. And so let me underline this once more. In dye-sensitized solar cell, the dye is not supposed to be a charge conducting film, so you cannot have it thick. For perovskite it worked. Now there are two differentiations to be made when we talk about the device structure. We have the conventional perovskite structure derived from the DSSC technology. It shows high efficiencies, but also we observe oftentimes pronounced hysteresis. The stability is not as good. Back then it was really bad, but nowadays, and I will give an example later on, we can make perovskite solar cells that are stable for over thousands of hours, but maybe not years yet in the field. And also the materials were a little bit expensive. You need to go through a high temperature step in order to make good titanium oxide. The inverted structure, so this is NIP. The inverted structure, which is PIN, showed a better stability, actually much less hysteresis from the get-go, but always had to fight with lower efficiencies. I think the current record is on the order between 22 and 23%, and came out earlier this year as well. And this is now a little bit more related to the classical OPV makeup of a cell. Now, in order to summarize this a little bit, what are the upsides and downsides? So yeah, this is another one that is not in the that I changed a little bit, but the content is more or less the same. We have on the plus side the low cost of the raw materials and the processing. You can integrate perovskites quite easily in tandem applications with silicon, with CIGS, also perovskite tandems, and you get very easily high efficiency. It's at the crossroad between organic and inorganic PV technology, which opens it up to a lot of different processing routes. Then on the minus and lead is toxic, as I said already. It shows some poor stability with respect to external stressors that are air, light, temperature, and water. So not the ideal case for a device that you want to put onto your roof. And then also the hysteresis, I mentioned it only in passing, but this is a typical instance of hysteresis where you see a change of the JV curve depending on your scan direction and the history of the cell. So what does this mean? It means that there is some inherent metastability built in these devices that changes as you measure it. So this will change a lot for your equation once you make it into a device and want to calculate the exact power output. But more so, it also carries some implications on the final stability of such a compound. And then, okay, so I don't know if I want to call this here a minus. It's a highly competitive research field. Again, a discussion we had over lunch. If how easy can you get into this into the research community? The amount of papers that come out is growing exponentially. Yeah, it's what it is. There is no guideline from my side to this. Yes, of course.
So in the previous slide,
yep.
So when you have the next one. So when you have
okay, I've got it on here.
So when you're sweeping the JV curve like in the forward direction, so you get less current out, like around 0.6. And if you wait for like a quite like a long time with the same bias, you get the amount for the reverse.
Yes, you are approaching it for sure. So. This is, of course, so there's, okay, so let me enter this discussion a little bit. There was an attempt to introduce a hysteresis index that is the area under this curve for each cell in order to quantify hysteresis. This has failed spectacularly because this kind of behavior is really depending on your scan speed. So if you scan very slowly, you may not see hysteresis at all because the processes, for instance, of ion migration, build up of an interphase layer at the interfaces, follows, either it can happen on a minute scale or the scale of seconds. It really depends on the interfaces that you design for the perovskite cell. But in general, in order to get back to your question, yes, if you would stay at the maximum power point, you will eventually approach the other part of the reverse curve if you first went thereby forward. Yeah. Again, it's not really clear on what causes the hysteresis, on what sort of time scales. Ion migration to the interfaces is being regarded as the main culprit for this. Okay. We now come to the fabrication of perovskite solar cells. To give you a very short overview on this, the wet processes are historically the first route developed, but they also use hazardous solvents like DMF and dimethyl sulfoxate. So this is a real issue when you want to go to large scale and safe production techniques. Also when you try to write proposals that do not get rid of these solvents. An advantage for us was that we could use coating equipment that was already there and established in many groups. That's also why so many groups from the OPV community could enter the field readily. And you have relatively short processing times. In the dry processes, however, you get a better reproducibility, usually a better homogeneity over a larger area, and automation is better possible than over here. The overall processing time, however, is much larger, and this plays into the cost of this vacuum process or dry process. Now, there are some rough differentiations that you can make. You have on this axis the wet processes, on here the dry processes. The one-step process, you have all the precursors, in this case methyl ammonium iodide and lead iodide, in the solution already. You spin cast it, you anneal it, and you form, after evaporation of the solvent, the perovskite. This is also what we do in our baseline standard process at IPVF. On the other hand, we have in the dry process co-evaporation of methyl ammonium iodide and lead diiodide. When you want to get into details about this and how well it works, I recommend you to approach Alex B later in this week, and he'll be happy to share all the info we have. The two-step process. Here we first make a film by PVI2 evaporation and then dip it into a solution of MAI, for instance, and see the conversion into the perovskite film afterwards. Usually the penetration and formation of this film is not as good. You can see a lot of the PVI2 precursor remaining in the film, which is not necessarily a bad thing, but needs to be regarded as an insular issue that you have to deal with. And similar holds for the two-step process. Again, if you want to know more about this, ask Alex. Further for the fabrication process, on your slides you have a few a short overview on what is out there. It started all with spin coating. Of course, here you're confined to a small area. You can spin coat only on substrates of a maximum centimeter size. So there is no way to make a module out of this process right away. But the ink processing means for ink processing and drying times and so on are critical in order to develop the other techniques, which are, for instance, doctor blading or slot die coating, which again is a technique that is really on the rise for a large area and large scale perovskite production. Moving on to the dry processes, we did really start with this co-evaporation. And don't be fooled, this is not a pure, or you can't see it as an MBE process. So this is still pretty dirty. Once you start evaporating from your organic source, you'll see your pressure rise, and you eventually get something that I, as a vacuum scientist, would rather call a CVD process. So this is something that we are also now trying to dial in real time. And then, of course, there are true hybrid processes where you start with your substrates that could be either evaporated or made by solution, and then you evaporate the organic precursor in order to convert your material. Okay, so I need to hurry up a little bit. Just to say that these processes can be combined with other deposition processes where you make your PVI2, for instance, by sputtering. So this works. You can also go to flash evaporating, and also very interesting pressure processing. And this is something where we use the powder, so mechanically ground perovskite powder that you could make into small presslings that make very poor performing solar cells that can, for instance, be used for radiation sensors if you just want to measure a photocurrent and need a macroscopic detector. Now, I said that I now added just a few things to this overview about where are the big development steps. I took this from Louis' paper that came out relatively recently, and maybe there are three big points to make here. Really, I described already, getting rid of the liquid electrode was key in order to make this technology, or bring this technology in the range of classical stability. Then it was composition optimization that made a huge boost from 10% up to 22%. You can see this is in somewhat chronological order, the difference between MA PBI3 that was started here, and then this cesium methylmonium formidinium lead iodide bromide mixture. While I was at NRO, we actually called this the kitchen sink perovskite, because you pour everything together, stir it up well, and then make a film, and it works as a perfect solar cell with 20-something%. And now, and this is actually interesting because so chronologically I wouldn't just put it here. This was something that was done again from the get-go interface engineering, as for other thin film solar cell technologies, is key, not just really to enhance the performance, but to improve the stability. So I can't stress enough on how important it is to shield these materials from external stresses, so ions that can migrate to the interface and induce electrochemical reactions as you operate your solar cell. So this is currently really also the focus of the work that we are following. In order to run you through the most important milestones, and I'm almost done. It was really the breakthrough by Michael Saliba, while he was in Michael Gretzel's group, to use these cesium-containing triple cation perovskites. And if you remember, I showed you before the Goldschmidt tolerance factor chart. And if you use purely formadium-based, formadium-lead iodide materials, you will see a phase transition from this photoactive alpha phase into the delta phase. Adding cesium brought it into the range of between 0.8 and 1 for the tolerance factor, and made it much more stable, as seen here for the device characteristics, and in red the cesium containing devices. And the next step, and again it was Michael, he introduced and incorporated rubidium cations. So this is not really the classical way on how you make your baseline reference device, I want to say, because particularly, as you can see here, rubidium lead iodide is outside of this tolerance factor range, and it is presumably not integrated into the perovskite lattice. So for us now, looking at the influences of all these different alkaline species or alkali species is a rediscovery of what people have already been seen and learned for CIGS. So we're very happy to merge these communities to some degree. But in any case, what Michael was seeing, that when he added rubidium and not knowing where it really goes, he could increase the performance, but also get to really long-term stability. With the caveat here that the stability assessment over hundreds of hours was done in nitrogen atmosphere. Now, the last 2 points I wanted to make is really perovskite solar cell stabilization with 2D perovskite interlayers. So you can actually start off with a 3D perovskite that has a PBI2 rich surface. And now you can start introducing these long chain molecules in order to make an interlayer that follows the 2D structure. It has the big advantage that these long chain molecules constitute an organic or a surface that is terminated with a closed shell electronic system. So it's not easy to attack the system chemically, and hence it leads to passivation of films. Also, the 2D perovskite, you can already see this from macroscopic material, are way more stable than 3D variants. And okay, so why not show a table with hundreds of numbers? Only pay attention to this one here, where PAI has been used in order to make a 24.65% cell with 90% power conversion efficiency, still achieved after 600 hours at max power point with continuous light soaking, just in order to give you an example. Now the question is, and I want to bring this question to the audience, can we make a purely 2D perovskite based stable high performance solar cell? Any idea, can we or not? Or what would be, okay, yes, who said yes? You're right, so okay, yes. What would be the problem that you see in this configuration, a purely 2D perovskite as a solar absorber in a cell? What could be difficult? Excuse me? You can make them with a relatively fairly small band gap.
High concentration of methyl ammonium iodide is present. So there is problem in charge transport.
Yeah, there it is. So charge transport is a big issue, right? If you have a layered film with these essentially carrier blocking organic molecules that are intercalated, you can't transport the charges that you generate. So what was key here is to adapt your production procedure and grow from the top these columnar structures, where you now have a 3D channel from the top to the bottom that is separated by 2D walls, so to say. And with this, you can make these complex cells. And again, a big table, but focus your attention on this device that has been achieving a 18.4% power conversion efficiency and had an, well, actually the stability wasn't as good, but it is promising because inherently you have a more stable perovskite cell. I want to raise your attention to one small detail here. It was used with PIE and interlayers on PCBM, so manufacturing the energetic landscape of your interface was key in order to allow this columnar growth. Now, this is the summary of everything. We are hunting for efficiency, stability, so I said this already, efficiency by integrating perovskites in tandem devices, stability by chemical passivation, but also encapsulation, and scalability. We moved from 20.3.6% for this silicon perovskite tandem device to 25.2%, and now, as I said, earlier this year, 29.1%. With no clear, well, I mean, of course, there are the limits we heard about, particularly the Schottky-Kaiser limit earlier today, but it's unclear on what is currently the limiting step here. We are introducing new interlayers with these interfaces in order to get closer to, or get to higher efficiencies. And when it comes to scalability, this is something that has not been regarded a lot, but there is actually a champion module annual chart where you can look up different modules categorized in module sizes and records certified by NREL. So the main optimization route is, of course, the interface. So this is a small teaser for tomorrow. First, of course, Uwe's talk, and then mine, where we'll discuss this part particularly. So just to show you here, we made tailored interfaces and could get extremely stable devices. So these were run without encapsulation for 1,000 hours with light soaking and current extraction, and only took a hit of 5% of the power conversion. So they remained at 95% power conversion efficiency. As said, we will skip, in the interest of time, the quantum dots. And so this was the outlook. We are looking at efficiency, reliability, and scalability. It was a long day today. So one word from our sponsors. Why convince at 7? So this is. I know. So, but so this is the only picture I found on ResearchGate. But you have a badge. So. But you have a badge, so yeah, okay. All right, and thank you very much for your attention.
So I propose to keep the questions for the drink. So the three next steps are drinks in the bar, below the restaurant at 7, dinner at 7:30. And posters after the dinner in the area just over here. So you will find everything. There are panels that you can move to put your posters, and that will be in this area. Okay? What time should we find the posters? Sorry? What time should we find the posters? When you want. Now if you are ready, or...